Good morning, grade 8. I hope you're doing great. We have a lot of people in the house. Sort of a lot of people in the house. 16 and rising, we'll see. I hope you enjoyed the bumper music. Jayla says, Liv says she's scared, and Lucy's laughing. What is that music? That music's called electric popcorn. If you have a choice for bumper music is the music you play before and after the presentation. Feel free to make a request. I will play your bumper music. All right, I'm assuming as many people are here as are going to be. We'll wait like one more minute. We keep adding. We're up to 19. I know we'll have one absence. Charlotte Dollinger's here, Lucy's here, Annabelle, Liv Ashley, Jack Mulvihill, Tack is here, Simon is here, Darby's in the house, Jayla, Liv, all right. We'll start in just a second. So it's Wednesday. We've lived through 3 days of this. I'm glad you're here. I appreciate your time and attention to your continued learning. And we'll certainly pour our time and attention into making your continued learning better. Olivia is here. Jack English is here. All right, well, let's start. It'd be a good idea today if you have your study guide that we passed out, because we're going to move from the people into the structure of DNA, and it's going to be a good idea to have somebody to take a look at. I can show it to you on the camera, but it's a lot better if you have the study guide with you. But let's continue. A real quick review. We were talking about DNA itself isn't alive. The chemical reactions that it catalyzes do define life and create life. Life has a problem. Cells have a problem, 2 of them actually, storing all this information that defines life and then replicating it and passing it on to the next generation. And nucleic acids / DNA, RNA are the molecules that absolutely solve those problems. We said that there were a lot of people who came up with the idea that DNA is the molecule. And we started a long time ago back at a Catholic monk who was working in the soil with his bare hands in Czechoslovakia, our friend brother Gregor Mendel. And Mendel becomes known as the father of modern genetics because he stares at pea plants, lots and lots of pea plants for a long time, and discerns, utilizing math, regular repeating patterns and how it is that flowers decide what color they're going to be, as well as how do the pea seeds decide whether they're going to be smooth, rough, or crinkly, the surface of the seeds. Those laws that he determined are applicable to any trait that is controlled by 2 genes or 2 alleles, and believe it or not, we still use them today. So Gregor Mendel, although he worked long ago during the American Civil War in Czechoslovakia, is the father of modern genetics. Our next friend, Fred Griffith. Fred Griffith spends his life killing lots of mice, and he does it using pneumonia. His first discovery is, what is pneumonia? Pneumonia is a bacterial infection, he decides, and he sees that there's different versions of it. He worked with a quote-unquote friendly version that only made you sick, and then another version that didn't make you sick. It killed you, and he saw that there was some unknown, non-living factor that could transform friendly bacteria into brutal, murderous bacteria. World War II came, interrupted everyone's investigation into what it could be. Even at the time, people were pretty certain that we only had 4 choices of what this non-living transformation factor could be. It would be proteins, lipids, nucleic acids, and carbohydrates, the very famous plank of the macromolecules. After World War II ends, people quickly turn their attention. The scent of a Nobel Prize is in the air. It grasps everyone's attention. Everybody and their uncle was trying to discover DNA. Avery, McCloud, and McCarty redo Fred Griffith's experiment. They use enzymes, proteins that chop things up, and they eliminate one by one the categories of proteins, lipids, carbohydrates, and nucleic acids. When they've eliminated proteins, lipids, and carbohydrates, the bacteria that are mean when they're dead can still transform the living bacteria. It was only when they eliminated nucleic acids in the form of DNA that they found that no transformation could occur. So voila, they've discovered that it is DNA that is the molecule of heredity. And now, on the horizon, it seems just an inch from everyone's grasp, is the idea that if we know the structure, we'll know how it works, and we can literally control life. Knowing the structure means that we can mess with it, and messing this time meant messing with the blueprints of life. People truly realize that if we know the structure of DNA, we will start a revolution. And they did. The race was on to find the three-dimensional structure. And we talked about that race earlier in class. We told you that Watson and Crick, James Watson and Francis Crick. James Watson is an American. I'm going to post a video for you all to watch. It's a TED Talk in which he's interviewed about the discovery. He's a character. He is still alive. He was born in 1928, which means he's 90 or 91. And of all of the discoverers, James Watson remains alive. He's controversial. He said some really, quite honestly, mean things about DNA and other people, indicating that he is possibly prejudiced or kind of a jerk, maybe. But that doesn't erase the fact that he has a story to tell about being on the cusp of science, being at the cutting edge when the DNA was formed. He's somewhat entertaining, so I'll post a video for extra credit for you to watch. It's a TED Talk. It's not more than 14 or 15 minutes, and I'll post that tomorrow. Do a little bit of extra credit, and I'll give you extra credit points. All right, that being said, we talked Watson and Crick are working using models. Great big, think of them as Legos, but they were metal. And, they were being sleuths. They were being Bond sleuths, not James Bond, but chemical Bond sleuths. They were constantly changing the shape of their model, trying to make it possible for every atom to have the exact number of bonds that it needed. They knew that at some point, if they kept changing the model, that it would be right. And when I say bonds, that carbon needs 4 bonds, hydrogen needs 1, oxygen needs 2, phosphate, its number, so on and so forth. And they were having a hard time figuring out, well, what does DNA look like? They knew that there was a brilliant form of technology called X-ray crystallography. It was a way of taking a picture of tiny, tiny things by blasting it with X-rays. In order to do this, it requires dozens, if not hundreds of hours of exposure time. And there weren't a lot of people that were really good at this technology at the time. At another university, also in England, was our friend Rosalind Franklin. And she is a female scientist. You have to really give her kudos. She fought her way to the top. She was a brilliant mind with this ferocious curiosity, and she unleashed it into the arena of science and colleges at a time when science and colleges were mostly males and they didn't necessarily want female professors, and she wasn't treated the best, which is sad, but that was, again, it was in the 1950s, certainly not making an excuse for it, but those were the times in which she lived, and yet she hung in there tenaciously and fought back and has truly made a name for herself. Her interest was X-ray crystallography, and what she liked taking pictures of. Ironically, in today's world that we're living with fear of the coronavirus, is she was interested in viruses. She was extremely good at taking pictures of these tiny, minuscule beasts that, as we're learning, can be so ferocious themselves. She was convinced and basically ordered to spend some time taking a look at a molecule that she didn't have a super amount of interest in, and that molecule was deoxyribonucleic acid. She was forced by her department to turn her attention temporarily to investigating the three-dimensional structure of it, utilizing her X-ray crystallography techniques, which were superb. She was at the top of her game. Wilkins was her boss, Maurice Wilkins, and he was also an X-ray crystallographer, but he wasn't nearly as good as she was. And one day, he went to go see what her work was creating, and without her permission or knowledge, he let himself into her office, went through her pictures, and found several that were just nearly perfect, and one which was perfect. And you all know by now that photograph that she took was photograph 51. And photograph 51 was few things in life achieve perfection. This one did. It was a picture of DNA at the perfect angle, with the perfect amount of light, with the perfect time of exposure, with the perfect focus. It was just brilliant. And people who could read X-ray crystallography could read the patterns of light and dark and deduce what DNA sort of looked like. If you happen to have a three-dimensional metallic model nearby, you could easily transfer the patterns of light and dark to your model. Well, Wilkins didn't, but he knew that Watson and Crick did. And so he got those two. They took the picture without Rosalind Franklin's permission, ran across town to the other college, and literally it took them 2 hours after they got the picture, just 2 hours, to rearrange the model. And then it happened. For the first time in the history of humanity, 3 human beings were peering at the exact structure of deoxyribonucleic acid. They weren't just looking at a model, they were looking at a vast gate that had opened up. Maybe it was Pandora's box that had opened up. Anything was suddenly possible for humanity. Changing life itself, creating life, editing life. We're still reeling from that discovery. We're still deciding what it means to us today. It's the year 2020, and we have yet to fully grasp what it means that we know this structure. How DNA behaves and how it transmits its knowledge is so complex that although it's been many decades since the discovery, we don't fully understand it yet. There's a mystery within a mystery within a mystery still of what goes inside of cells as the DNA controls things. So if you think everything's been discovered, why should I be a molecular biologist? Well, you're wrong. Like, we are just at the cusp of understanding how to make things work, and there's plenty of room for people who are interested in this and who have a heart and will use it properly and ethically. All right. So those are all the people that we would like you to know. 1s, 2s, 3s, 4s, or 5s, check in with me. How much do you get all the people? Like, 1 is, yeah, I don't understand any of them. And a 5 is, yeah, I get this story that leads us to the discovery of the three-dimensionality of DNA. Check in with me on live chat. 1, 2, 3, 4, or 5. Awesome. Lots of 4s and 5s. I'm glad Emma Deal joined us. Just kidding. I know it's Maddie. Awesome. Everybody seems to get it. I was listening to Linkin Park just last night, Magdalena. All right. Awesome. Hi, Anne-Marie. Good to see you. All right. So let's continue. First off, you sort of need your study guide, all right? And you would be on the second page of your study guide, so flip it over. Does everybody have their study guide? Take your study guide out, look at the second page. On the back of it, there is a picture of ribose. It looks sort of like a stop sign, missing a sign. And then there's a square that says carbons. Why are they famous? And if you take those out, we can go from there. Katie, I see that you're online too. Don't you worry. God bless you, honey. Don't sweat it. I totally trust you. All right. 1 sec. I'm waiting. Trying to get you a picture. I'm going to migrate to a different platform, which is going to allow us to add some pictures and stuff, hopefully by next week if we're still all doing this. I don't see how we won't be, it's weird, I know. But we are going to keep being normal and keep our pattern and keep learning, and we are not going to let our lives be stymied by all this crazy stuff going on. Trying to get you a picture up. Oh, all right, here we go. Scratchy. No, I think I might try to use Zoom. We'll see. I got Switcher to work really well. Only the resolution is so incredible that you can see inside my pores, and it frightens everyone, including me. All right, here we go. Take a look at this. We're going to talk about what did Rosalind Franklin, Wilkins, and the gang discover? What is the structure of DNA? Overall, you need to know this phrase. They discovered that DNA is a double helix. So that's the big famous name for the shape of DNA. You'll need to know it for high school next year. If you're going into sciences, or you want to be a doctor or a veterinarian or a physical therapist or a nurse, you're going to hear the phrase double helix over and over and over, because every year you learn about DNA. And that's what they discovered. They discovered that DNA is a double helix. In order to think about a double helix, you have to think about a ladder that I would use to climb up on my roof. And if I take that ladder, and I take one hand and hold it on the bottom and one hand and hold it on the top, and I twist it so that it's sort of like a candy cane, then that's exactly what a double helix is. You get the idea that if I twist the ladder so that it's like a candy cane without the handle, that I have two sides, which we call the backbones, but I still have the rungs in the middle that I was going to use to climb up the ladder that I can't now. If you've ever gone up or down a spiral staircase, if you put both hands on the railings that you use to hold yourself so you don't fall, that's sort of like DNA as well. It's a spiral. So a helix is another name for saying a spiral. All right? I'll show you some pictures of it in a bit here. As with all of the macromolecules, they're made from single building blocks. They're made from monomers. And I glue or bond lots and lots and lots of smaller molecules together to make a huge molecule called DNA. So DNA, nucleic acid, or RNA, they're all really huge macromolecules, all right? chains of other molecules. And what are those monomers? What are the building blocks? Well, a note that we started when we were in class the last time we were together, and I actually miss you thinking about that, is that the monomers of DNA are nucleotides. Nucleotides, nucleotides. A nucleotide. And we told you that nucleotides are themselves made from 3 ingredients. I'm at the top of the page, on the second page on point 6, all right? And I'm reading you, nucleotides are made from 3 ingredients. They're made from a 5-carbon sugar, a triple phosphate group, and we know that phosphate is PO4, and a nitrogen-containing base. And we all talked about what phosphate groups were. We talked about bases as well earlier. So there's 3 ingredients to every single nucleotide. You have a 5-carbon sugar, and then you're going to have a triple phosphate group, and then you're going to have a base. And I have to bond all those together, and once I do, I will have a single building block for DNA, a single building block, the monomers, all right? I'm going to make 2 chains. I'll make one, think of a whole bunch of beads on a string, and I'm holding it in my left hand. And then I'm going to make another chain of nucleotides, and I'm going to hold that in my right hand. And then I'm going to hold them close together. And I want you to imagine that each pearl is now going to reach its hand out to hold the pearl next door to it. So I have 2 pearl necklaces. I'm holding them up side by side. They imaginarily have hands. And the pearl on my left hand holds hands with the pearl, the necklace that I'm holding in my right hand. And if you substitute the idea that they have hands with bonds, hydrogen bonding, then you know how these 2 side chains link. And when they do link, they cause this, they link at sort of strange angles, which causes the whole thing to bend, which makes it look like a ladder that's been twisted by a giant. All right? So let's move on down and take a look. Underneath point 6, we suddenly start to do paragraphs. All right? And underneath point 6, I'm taking a look at what the sugar is. So let's look at the 3 ingredients of a nucleotide. And we're coming close to the end of our time together. So the first ingredient of a nucleotide is a 5-carbon sugar. We drew that in class. If you take a look at your study guide, I have drawn a 5-carbon sugar there. And if you take a look at it, for DNA, the 5-carbon sugar is deoxyribose. And for RNA, the 5-carbon sugar is ribose. So for DNA, deoxyribose, and for RNA is ribose. But let's just sort of pay attention to DNA right now. I drew ribose. A sugar we told you in class it has carbons, hydrogens, and oxygens in this ratio. CH. Oh, I can't even draw. The famous sugar that you know is C6H12O6. Which obeys the rule. Am I frozen now? How about now? Am I frozen? Am I moving? It won't necessarily be that I freeze. It may be that I just freeze at your house. Some people are reporting that I've frozen. All right. Yeah, I think that's just a per house issue. Everybody's ability to stream. Maddie, am I frozen to you? All right. I'm going to go ahead and show you this. This is, so sorry, CHO 1 to 2 to 1, C6H12O6. All right. And C6H12O6 is glucose. CHO 1 to 2 to 1 is just any sugar. The sugar that we're using is ribose. And I'm going to remove an oxygen so that it becomes deoxyribose. Go ahead and put your finger on the sugar that I drew in the middle of that page near the square. That is deoxyribose. In class, we talked about how when we draw it, it sort of looks like a house that a 5-year-old would draw. You know, it has a roof, and then it has a satellite dish carbon. And if you notice, every single one of those carbons has hydroxyls and hydrogens attached to it, and that's just deoxyribose. It's a sugar. I'll ask you to pay attention especially to the fact that they've numbered the carbons in a counterclockwise, well, no, actually it goes in clockwise fashion, doesn't it? They numbered the carbons in a clockwise fashion. So if you look at the oxygen on the roof, in order for us to talk about which carbon is which, they numbered them. So you have the number 1 carbon. We actually call it 1 prime. Then there is the number 2 carbon, the 2 prime. Then there is the number 3 carbon, the 3 prime. And the 4 carbon, or 4 prime, and the 5 carbon, or the 5 prime. That is the starting place to make a nucleotide. And a single nucleotide is the building block for DNA. I'm going to take this starting place. Here's where things get attached. I facetiously, jokingly said it makes the carbons famous. I don't know that they're famous, but we can go with it. I'm going to direct your attention first to the number 2 carbon, strangely enough. And if you look at the number 2 carbon and compare it to everybody else, every carbon has a hydroxyl group on it. And it is at this number 2 carbon that we've removed oxygen, hence the name deoxy. D to remove, oxy, what is it that I did remove, and from what? Ribose. Deoxyribose. I've taken oxygen away from the number 2 carbon. All right. Last thing we're going to do today, because we're almost out of time, is I'm just going to go over why the carbons are famous. The number 1 carbon. You know that when I make a nucleotide, I'm going to attach a base, another molecule, to this deoxyribose sugar. Where does that base get attached to? That base gets attached to the number 1 carbon. So the number 1 carbon is going to hold a base, and that's why it's famous. The number 2 carbon is missing a hydroxyl group. The number 3 carbon is going to link with another nucleotide below it. The number 4 carbon, not famous. Not at all famous. Nothing to tell you about it. The number 5 carbon, is going to have 3 phosphates on it, and it's going to be used to attach to other nucleotides to make a chain. So now you have the basics of what a nucleotide is. A nucleotide is the building blocks of DNA. And to make one, I take deoxyribose for DNA. I attach a base to the number 1 carbon. I remove an oxygen from the number 2 carbon. The number 3 carbon is going to quote-unquote hold hands with another nucleotide. The number 4 carbon, nothing. Just nothing. Got nothing. The number 5 carbon, it has 3 phosphate groups on it, and it's also going to be used to attach to another nucleotide. And we're going to stop there. All right? Because we always do about 30 to 35 minutes and spend the last 15 doing some logistics. So, logistics number 1. 1, 2, 3, 4, or 5. How much do you get what we did today? What is a nucleotide? Where are you at? 1, 2, 3, 4, or 5. And if you're a 1 or a 2 or a 3, what questions do you have? All right, 9 of you reported in. I'm missing only 11 of you. Yeah, we'll get to science fair in a second, Lucy. All right. I don't know why people aren't reporting in. Possibly they're gone, which would be sad because it says there's 20 of you here. All right. So next, does anybody have any questions? Yeah, and I know Katie's on and can't do it. And no, I can't see Ella, but I'll count her as here. Thank you, Olivia. All right, anybody have any questions about the material that we've done over the past few days? If you do, awesome. If not, don't worry. All right, so I'm assuming you don't because nothing's popping up on my screen. I do have like a 10-second delay. Yeah, that's okay. If they're on their iPads, that's cool. Yeah, but they come in and they do count. iPads count in my total number, but I don't see their names. All right, my friends. Logistics. First, science fair. Today is, I need everyone who got accepted to LRSCF to register and attend electronically. Since we make up literally 94% of the entire Louisville Regional Science and Engineering Fair team, our little school is the team. So that if we don't go / electronically, it's going to look really, really bad for our school, for me, for you, for LRSCF. I know it's crazy times, but if you're not sick, I do need you to do that. Has everybody registered? Lucy, what questions do you have? Forged my name. Everyone at the Kentucky Science and Engineering Fair realizes that's happening. They don't care because they know you can't see your teachers. All right, Lucy, question about science fair. Thanks for checking in. Yeah, here's what happened with the fees. Is their website is connected to you're not officially registered unless you've paid your fee algorithm, and nobody can change that. What they've said they would do to get it refunded, and I think it's just $10 or $15. It's not. I don't think they're like breaking the bank on it, but they will refund it to you because it stops. From my understanding, it stops you from registering if you don't pay it. And I know it's silly because you're not going to get a lunch and you're not going to be there and, blah, blah, blah. But that being said, it's just one of those weird things that's happening because we live in weird times and we're not really going to the fair physically. All right? Does that help? All right. Now, I said I would. Is that good? Does anybody else have any science fair questions? So the expectations. All right, and then Maddie, I don't know what they asked for. Did they ask for a picture of the board or did they ask for a PowerPoint? Did they ask you all to create a PowerPoint? Is that an option that they've given you? Okay. They need to be able to see the material on your board. They need to be able to see the board. The pictures, everything. And what some people have done, is to create a PowerPoint, and the PowerPoint is made from images that they took of their board, right? And when they got to places that had things that were graphs under graphs under graphs, they went ahead and just took pictures of all of those things. So their PowerPoint is just photograph. It needs to be able to be readable. If you take a picture of your board and the judges have to use their fingers to make the screen larger because they can't read anything, chances are they're not going to read it. How did they say you'd be participating? Are you going to be interviewed personally, and or are you sending videos? What are the options that they gave you? Interviewed personally. All right, how's that going to go? Is it a Skype? Is it a phone call? Zoom, and Lucy's saying that too. All right. They said to make sure you had the whole day free, because at some point they will call you. They will connect you to Zoom, and you will give your presentation. So it'll be live. And I think that's probably the best, because then they can ask you questions, and so many of you really, really shine when it comes to answering questions and dialoguing. I'll call them. I agree. The information's been kind of crazy. So, in terms of homework, let's see. We've been DNA is a macromolecule. Another way of understanding it's not really super. And a polymer is a molecule made from many monomers. Yeah, Maddie, would you send me the email? Thank you. You all did. What questions did you all do last night? Yeah, 1 and 2. All right, so homework is 11 through 23. Homework is 11 through 23. And I'm asking everybody to email it to me. So homework is 11 through 23. And then email it to me. Sound good? And then we had dialogued about whether we were going to teach Thursday and Friday, and we won't. What I'm going to do is give everybody Thursday and Friday off, because 99% of you all are would need to work on science fair. They're asking for a PowerPoint, so you're going to need to take pictures of your board or scan it, or just cut and paste the text onto a blank PowerPoint slide. All right? And instead of meaning to do DNA class, I'm kind of feeling yucky, so I'm going to take Thursday off just to rest. I don't know. I'll take a look at the Anne Marie. I don't know when the PowerPoint's due, But Maddie's sending me an email she got, and I'll take a look at it. And, look on Schoology, and I'll post stuff, and then I'll alert you all, and you all can use your famous text messages to let each other know about the information, all right? We get the PowerPoint to them. How do we send it to them? I don't know. Wish I did. I'll try to find out for you. But for sure, in terms of logistics, look on Schoology every day. I might have something for you to do. I do plan to post extra credit opportunities. The TED Talk with Jay, I'll send it out to some of you all that text to everybody. And here's a question. Where's William? Does anybody have William's phone number or an email or a way to get a hold of him? I'm not mad. I'm just worried. Anybody have a way to get a hold of William? Annabelle, will you get a hold of him? Because he has, he's missing in action, I think. And have him call me or text me. All right, Annabelle and Simon, because Miss Lane needs to get a hold of him. Miss Whitfield needs to get a hold of him. I just don't want him to fall behind, because it's going to be critical, important, because it's all we have to grade. It's all we have for attendance, and so it's super important. So if you all could send me that, text me any phone number or email you have, it would be awesome. All right. Thanks, Annabelle. God bless you. I saw your mom at Kroger's. Annabelle, feel free to get a hold of me. Logistically, you're going to email me 11 through 23 before the day is over. Feel free to get a hold of me. Logistically, you're going to email me 11 through 23 before the day is over. Not teaching Thursday and Friday, but I'm back on, ready to go Monday at 10:30. I might get a hold of you with current events or having a meeting for science fair, but I would let you know on Schoology, as well as getting a hold of people that I know that can send the message out with the smoke signals of your electronic media. So God bless you. Thank you for being here. Thank you for caring. Thank you for not letting the world be turned upside down, turn your world of education upside down. Keep it the same with values and kindness, and love one another and love your parents, and we'll all make it through this. All right. It's great to be with you. I miss you. I just do. It's weird. I don't like it. But it's great to see your names pop up, and you are inspiring in your dedication to this, and I will see you for sure on Monday. You have 2 days to do your PowerPoints and science fair. Please, please do that. Get a hold of people that if you notice they weren't on today, and tell them that we're really, really pushing science fair. I need the people who got invited to go. God bless you all. I'll see you on the wire next time.